the molar mass lab. I've got the equipment behind me. I've got a hot plate, a 1 liter beaker, and we're gonna cheat a little bit and get started more quickly with some hot water. I'm gonna put 600 milliliters in here. Now I still put some boiling chips in here just to make sure that it evenly boils if it does reach the boiling point. And now we need to put 3 or 4 boiling chips in there. Turn the heater on 5 or 6, pretty high setting there. And I'm using a 250 milliliter flask. I don't know what the volume of this is. It might be 260, 255, or whatever. At the end of the lab, we're going to measure the volume accurately. Okay. Now, we're going to put a single boiling chip in here. Okay. And that's just to make sure that the liquid volatilizes very well. And we also use a single sheet of aluminum foil. And later, when we have the liquid in there, we'll give a single poke through the aluminum foil just with this piece of paper clip. All right. So I'm going to weigh the empty flask and show you what the readings are here. Okay, that's your important data there. All right. Now, we are trying to figure out the molar mass of this, so you're not going to use this number in any of the calculations until you get to the very end of the lab when you need to do a percent error and compare how close were you to this value here, okay? But this is the Lewis structure, well, a bond line drawing for this thing called ethyl acetate, and it has the formula C4H8O2. The molar mass is around 88, so we'll see if we're close. And the boiling point is less than 100 degrees Celsius, so that's great because boiling water will be able to sufficiently volatilize this, okay? Now, to do this experiment, you put sufficient amounts of liquid into your flask. I'm going to choose about 3 milliliters or so. Now this guy has a flammability rating of 4, you can see here on the symbol, and so it's the red number 4 there, so we want to keep this far away from the hot plate, especially if you're using a Bunsen burner in your lab. So we'll put this guy over the flask, we'll grab our needle or paper clip in my case, and poke a single hole through the top. All right, and we want to clamp this over the beaker. And so right now there's air inside of that flask of course. And when this liquid heats up, it will like turn into a gas and vaporize and explore that volume. And when it expands, it'll push the air out of that hole, okay? So when it reaches, when it all evaporates, ideally inside that flask will just be 100% vapors of this substance called ethyl acetate. And we will then remove it, cool it with some cold water, okay? And then we'll weigh it. Now, what will happen when it cools down is that those vapors will condense onto the sides of the flask and come down, And you'll see a little bit of liquid in the flask at the end. I'll show you what that looks like. All right, so this will take a little bit of time for this to heat up. Now we also have a thermometer to measure the boiling point, or measure the temperature of the water. And that temperature of the water is going to be the temperature of the vapors inside this flask, assuming it's all at thermal equilibrium. Okay, so I have a Celsius digital thermometer, so it'll be easy to read. And we'll clamp that in position. Now I already smell the organic vapors that are being produced by this apparatus here. Ethyl acetate has a pretty strong kind of smell, similar to nail polish remover, maybe acetone. It has that similar kind of smell. Just want to make sure the thermometer is not touching the bottom of the flask or the beaker, because it'll, register too hot perhaps. Right now you can see a little bit of bubbles occurring at that boiling chip now. Okay, so it's going to take a while for that 3 milliliters or so to volatilize, and so it has to heat up and get out of that little hole at the top of the aluminum foil. And so once that's complete, we will go ahead and move to the next step of the procedure. Now we don't want to read the thermometer right now. I'll turn it on though. It's reading about 87 degrees Celsius. It doesn't need to be 100, it could be, but we'll read whatever that is. So remember that the volume of your gas is going to depend on the temperature and also the atmospheric pressure. So we have a barometer in the adjacent room that will read the pressure in this actual room here today on this pretty sunny but cold day. So who knows what the atmospheric pressure is. And so that single boiling chip in the Erlenmeyer flask there just assists with this being a gentle boiling and giving it more surface area to evaporate and boil more rapidly. Ideally, you want the water to be a little bit more, so I'm going to go ahead and boil some more water here and put maybe 100 more milliliters in there. When this lab is filled with students at their different workstations, all doing this experiment, the room can be filled with quite a few vapors. So it's nice that I'm the only one in here, and of course we can run the fume hoods, but that's a little bit noisy for the camera. All right, so you can top this off a little bit here. It's hard to know beforehand how much water you really need. If we fill up the beaker too much and we put our flask in there and submerge it, it'll displace too much water and it'll flood out. So I like to top it off like I just did. I still see a couple milliliters in there, so maybe a milliliter, so we'll keep on waiting for this. Okay, Temperature is 94.3, so that's sufficient to volatilize or boil this substance. And it is boiling in there. The water is boiling as well. You can hear it rumbling in there. But that's right on the surface of the hot plate. The thermometer, which is about a centimeter or so from the bottom of the hot plate and towards the side of the beaker, is reading only 96 degrees Celsius. So the best position to place the thermometer would probably be right next to the flask. Because that's where our flask is. So it looks like all my liquid has evaporated now. Oh wait, not yet. Now what I'm looking for are small little droplets form on the sides of the flask and fall down. When this vapor volatilizes, it comes up and it condenses onto the cooler top of the flask and then dribbles down the sides. You can barely see these small little lines of liquid forming as they're coming down. So I'm waiting for that to go away. That would suggest that it's all gas in there and that there's no liquid left that needs to be volatilized. And when that point has been reached, then we'll pull this out. Definitely is hot enough, but this process is controlled by kinetics as well, so it just takes a while for this liquid to evaporate. Now, if you wait a really long time, it's possible that the air could diffuse in through that pinhole and displace some of your vapors, and you'll lose a lot of the vapors. But if you pull it out too quick, maybe the aluminum foil has captured a couple drops, or maybe there's still some liquid on the side, or even a big puddle on the bottom that didn't volatilize correctly, completely, and so your mass will be way too high. So it's tricky kind of to get this at the right point, and we're just using very primitive glassware here. There's a smudge on the outside of the glass. I think we're good with this, so I'm going to go ahead and read the temperature now. Okay. And I believe that is visible on the camera. Okay, that's your temperature there. And now, as I mentioned, we're going to cool this quickly because we don't want the gas to escape, the vapors to escape. So we'll pull this out and we will cool it down. This is Pyrex glass. Pyrex is designed to have a low coefficient of expansion and therefore not shatter when it's cooled, rapidly from a very hot temperature. So that's why we use Pyrex glassware in the lab. And you have those glass pots and pans at your house, maybe, if you use that kind of material to boil, water for spaghetti or something like that. So that's also Pyrex. So this ensures all the vapor returns back to the liquid form within my flask and does not diffuse away. And it also speeds up the lab a little bit quick, so the video is not as long. You can't weigh something that's really hot. You gotta weigh it when it's cool, okay? So I'm gonna dry this now with a towel. Now, if you fail to dry this, you run into problems, because you'll not only get the balance wet, and your professor might get a little mad, but your mass will, of course, be way high if you have water here. Sometimes when you boil water, there's steam that can condense underneath the foil, so you got to look to see if that's a problem. In my case, I do not believe that's a problem. Okay. I don't know if you can see this on the video here, but there's a small amount of liquid in there. Now, trust me, there was not that liquid in there when I took it out of the flask. Okay, it was a boiling chip and it looked completely dry in there. So that's the liquid ethyl acetate that has condensed. Now again, we'll weigh the apparatus here. So it's the mass of the flask, the foil, the boiling chip, and the condensed vapors. So that technically is the mass of the vapors. Okay. I'll position the camera over here to make a reading. Okay. All right. Now let's do a second determination. The second determination is even faster because our apparatus is all set up. It's hot. It's ready to go. We just put a little bit more of the ethyl acetate in here. I don't see any water vapor around the edges here, so it looks pretty good. And I'm just going to reuse this foil here. So I'm assuming that the flask and the boiling chip and the aluminum foil are still the same mass. Okay. So you can use the starting mass of the flask for your determination. So I'm going to put maybe 1.5 milliliters more of ethyl acetate in there. And again, I'm going to put this far away from the hot plate because I don't want to make a safety video right now. All right, so we'll clamp this in position. Make sure it's firm in there. Submerge that guy. You don't want to do too much because you might make the flask kind of pinch down on the glass beaker and cause a crack or a break. Go ahead and put our thermometer in here. And we'll position it next to the flask. And we will wait. I should have used a fresh boiling chip. These really can't be reused, but I'm going to go ahead and do it anyway. I just noticed my boiling chip is not in the corner of where the liquid is, so try to get that down in there. All right. Yeah, these boiling chips kind of get deactivated after you use them. So for like right now, it's in boiling water, it's working, but I can't collect those boiling chips, cool them down to room temperature, and then use them somewhere else. They kind of lose their efficiency. So, but it'll volatilize and I just have a small amount of liquid, so I'm confident this will still work. All right. So this is trial 2. We'll read a different temperature for trial 2, and we'll get a different mass for trial 2, and then you can do all the necessary calculations. Well, that's not true. I need to measure the volume of the flask, and I need to measure the pressure of this room. So we don't want the water too hot and boiling really bad, because it'll produce a lot of steam, and it tends to get caught underneath this aluminum foil. So just a nice, hot temperature is good enough. If you see it boiling a little bit too vigorously, you can turn off your flame or your hot plate. It's definitely a source of error in this experiment. We're at a temperature of 96 degrees. I still see minor amounts of condensation on the insides of the flask near the top on the back side, so I'm waiting for that to disappear, at which point I'm going to assume that there's no more liquid within this flask. It's all 100% vapors. Temperature is still 96. Normally I use a substance which is much more volatile. It has a lower boiling point by about 15 degrees Celsius. This guy here, when it evaporates, tends to condense around the top parts of the cooler flask that is not submerged below the water, and so it just keeps evaporating and condensing and evaporating and condensing. It doesn't seem to want to come out of the pinhole. Normally a procedure would say let it go 5, 10, 15 minutes, something like that, or until it has just disappeared. The liquid has just disappeared and it looks dry on the bottom of the flask. And that's in the assumption that your substance is very volatile and won't condense and trap around the top and comes out. This one has a little bit higher boiling point than I'm accustomed to, so I just want to make sure it all volatilizes. It's just still condensing on that tip there. I'm gonna put some more water in here. Let me show you what it looks like from my vantage point and what I'm looking at here. Can you see those droplets forming down the sides of the flask? You see those little drops that look like they're going down, like they're dripping in there? That's on the inside of the flask. And so we want all of the liquid to volatilize and be replaced by vapor. So try to fill this up even more. Don't dare go much more than that. We'll see if we can get this stuff volatilized. Still 96 degrees Celsius. I can smell a much more strong odor of ethyl acetate now. So I think that is causing it to volatilize better. There's a little bit of condensation on the side of the flask up there too, on the outside from the steam, so I'm just trying to wash it off so I can see the insides a little better. I think we've got it all now. Side. So I'm gonna let that go about 5 more minutes, then call it quits either way. The small remainder of liquid in there is just very minor compared to that large volume of liquid we saw that formed when all of the vapors condensed. So I think it's probably like a 1 to 5% error. That's my guess. But I don't want to prematurely end the experiment, do the calculations, and find out I have to redo the whole video. So I'd rather just wait a little bit longer. I know I'm not waiting too long, such that all the vapors are going to escape out. So we'll just wait a couple more minutes here and then cool this and go from there. My eyesight's not the best, but I think we may have that. I would suspect that this kind of problem was happening with the trial 1 too. I just maybe didn't notice it as well. And so I'm suspecting that trial 2 is going to be better data for our determination of the molar mass of ethyl acetate. So again, we'll just wait 1 more minute here and then we'll go on. All right, I'm going to go ahead and just terminate the experiment. This unknown has a pretty high boiling point, and that probably is leading to some error that we would expect. Okay, so let's read the temperature first. Whoops. I do hope that was visible on the camera before I dropped it in there. And we'll take this out. We'll quickly cool it with some gently running cold water here. And this is why I like to have this on a secure clamp, so you don't have to burn your hand holding a hot Vernier flask. When the vapors condense and turn back into liquid, of course, air from the atmosphere comes back in through that pinhole so that you don't have a vacuum. So you need a pinhole to let the vapors out, and then you need a pinhole to let the air back in. We can't completely seal the flask here. Water's pretty cold. I think it was like 40 or something this morning. So that's good. We'll dry that now. Want any moisture present on anywhere on this flask. Of course, from the boiling water, the water that was used to cool this, and I like to peek behind the foil there and see if there's any condensation. It does not feel wet under there, so I like that. All right, and so we'll go ahead and weigh this. this time around it looks like less liquid in there, so like I said, it might be a better trial. So there again is the liquid in our boiling chip. Okay, so balance is reading 0.00. That's great. I'll put that on there, and we'll measure the mass of the vapors. Okay, so that's the weight there. Now what we need to do is determine the volume of this creature here. Let me dump out the vapors. The vapors, the liquid is organic, so it goes in the organic waste. And now I've got some nice, cold water here. It's just tap water. And what we want to do is measure the volume of this. I know it says 250 milliliters on there, but that's just not really a high accurate piece of glassware. So what I like to do is, perhaps we'll do this a little bit away from the balance. I fill this up to the brim here, right up to the top there. That's where all the vapors would fill up the flask. And then I pour this into here. This can hold 500, so that's double the size of this. So I quickly pour this in here. And now we want to crouch down and read the volume here. Now, just a word about this graduated cylinder. The 500 mark is, let me see if I can position this good. So the 500 mark is here, okay? And this is 450. So each big line here, each line here is, I believe, 5, okay? So 450, 55, 60, 65, 70, 75, 80, 85, 90, 95, and then 100, okay? So 500, okay? So each one of these is 5 milliliters. So you kind of have to do a lot of estimating there. I would not be able to read this more to plus or minus 1, okay? So you're gonna read 251, 252, 253, or 249, something like that. So I'll position this near the this guy here. Okay. And so you can see how it's definitely above 250. 250 is right there where my fingernail is. And so, not sure if you can see this well. I'll take a picture and make a freeze frame in the video, okay? So we've got the temperature of our vapor, we know the mass of our vapor, we know the volume of the vapor, and now I'm going to go into the physics lab and measure the, barometric pressure. So it's a good thing that this is in the room. I know you can go on Google and search for the day's pressure, and they'll usually give it to you in inches, okay? But let's see what we got here. So this is the physics lab. Definitely has a different kind of smell than the chemistry lab. And on the wall here, I have what is called a barometer. So down here you have the mercury, okay, it's filled in there. And inside of this metal protective tube is an upside down tube of mercury. And the way you read this is on the left is the centimeters column, okay? So atmospheric pressure is about 760 millimeters, right? So that would be 76 centimeters. So 76 is right here where my finger is, okay? And then you have what's called a Vernier Scale. Now the weird thing about mercury is that the meniscus is upside down. It's not like that, it's like this. So I position the line on the top of that, and then you have to read the left scale to see which number lines up with that to read the next few decimal places. So let's do that. Okay, so not sure if you could see inside this tube how it's very shiny in there. Let me take this off the top so you can see there. See my hand behind there? So there's mercury up to about right here. And so we'll position this scale. It's the hardest thing to do with the phone. Okay. So it's about right there, okay? So if you look at this guy here, you can see that it reads 77 would be right here. So it's pretty high pressure, okay? 760 would be normal atmospheric pressure. It's reading 77.1, and then it's between 77.1 centimeters and 0.2. So it's between 77.1 and 77.2. So what is that decimal place? What you do is you look to see which of these lines line up on this movable scale. So it goes between, 0 and 10 here, 0, 5, 10. So you look to see which of these small little lines line up. It looks like the fourth one is lining up pretty good, okay? So we would say that this is 77.14 centimeters, okay? Does that make sense? 774.1 millimeters of mercury, okay? That's what I get right here on the wall. So, and this is next door, so it's in the room with the air circulation system on and everything. So now we know the temperature, we know the pressure, we know the volume, and you know the mass. So now you have all the information needed to calculate the molar mass of the gas. At the end of the experiment, you're going to compare it with ethyl acetate, the known mass of ethyl acetate, okay? And that's the lab. I'll take a picture of the graduated cylinder and give you that information. I'll show you the bottle one more time in case you need that, okay? So thanks for watching. I guess this is our last lab of the year, and I'm sorry you couldn't be in the lab. One of the things that really interested me as a science student was getting in the lab and doing experiments. Ever since I was a kid, I was trying to find all kinds of chemicals underneath the cabinet in my house and collect the elements, around the world, from broken radios and this and that and the other thing. And I was just always hands-on, and I feel sad that you can't be here to do things hands-on, to experience, setting up equipment, reading thermometers, and seeing mercury, and stuff like that. But anyways, this is the last lab, and from all this data, you can calculate the molar mass, and I hope you have a good winter break, and we'll keep on doing labs online in the spring. Take it easy.